All right, guys, so let's start. Good. So look, what do we know? What we don't know. So we know that if we want, well, first of all, right, do you have any questions about the grading system for this semester? So did you get everything from it? Did you read it at least? Yeah? No? So we don't have assignments for this semester. We only have tests. So we have tests, the middle term test and the final test. And this is about the 60% of the final grade. And then we get 10% of the grade from attendance to the class and 30% from the exam, final exam on theory. All right? So let me write that over here. So look, we have, all right, yeah, like 30% is from test 1, 30% is from test 2, okay? Then we have 10% from attendance. And what else? 30% is from for its final exam on theory. Okay? So that's the way we'll do it. So you can get from each thing, you can get from, from 1 point, from 0 points to up to 3 points, and you can get only integers or, I don't know, 2.5 or something like that. So half, all right, or 1.5, 0.5, or 2, or something like that. Nothing else, okay? And if your final grade is something like 6.5 and you want 7, then you need to solve a simple problem on probability, of course. And yeah, simple, but like good enough, right? And you can get your 7. And if you don't solve that problem, then you get 6, all right? I think everything is clear. Good. Okay. Now, look. So, any questions? No? Good. So look, we need, what do we need? Every time. Let me just remind you that because we need to remember that every time. We need to understand this, right? We need to understand every of these subjects. And the first one is the simplest one, just any set, right? So omega is just any set, this is the sample space. But then we have F, and this is the sigma algebra. And of course, we can just define what the sigma algebra is, like we already did before. So we know what the sigma algebra is. So could you please remind me which are the properties of a sigma algebra? So the sigma algebra is a family of sets in which what? So what's the first condition of a family of sets to be a sigma algebra?
Well, it has to be closed under complement, like complementation. So if X is in sigma algebra, then it's complement.
All right, so this is the second one, right? So if A is from F, then the complement of A is also from F, right? Good. So omega is an element of F, yes?
And it's closed under countable union.
And it's closed under countable union. So if we have some collection AI, then we know that the countable union is also an element of F. So this is the definition of a sigma algebra, okay? But how do we get such set of subsets, right? How do we get it? To do that, we need, so this set is very complicated, very complex, right? We need something not that complex, okay? And to do so, then we need to start with some simple set, and then everything will be getting more and more complicated, right? So the first set that we know that we already constructed is a semi-ring. So, right, we have a semi-ring. Yes? And then, from the semi-ring, we got something called a ring. So we got a semi-ring, and then we got something called a ring. But a ring is more complex than a semi-ring, and we already know that a ring is a semi-ring, but a semi-ring is not a ring, right? So how do we get, and then the next question is, how do we get from a semi-ring, how do we get R of S? So let's call S the semi-ring S. How do we get the minimal ring containing S? So R of S. How do we get that? So we know that R of S is just on all the possible disjunctive unions of elements. Okay, so of elements of, how to write this? Just a sec. Yeah, so I, and I is a subset, here a subset. No, wait, I, capital I. So all the disjoint unions of elements of S, so this is an element of S, and we say that S has n elements, right? So we take all the possible elements of S, we unite them, and then we'll get R of S. So the minimal, so this is the minimal ring containing S. Okay? So all the possible disjoint unions of elements of S. Then we have a semi-ring and we have a ring. So we got this, and we know the very unique good example that we have is the semi-ring of the half spaces, right? So let's take the following semi-ring. So all the half spaces A and B from capital A and capital B, right? So we can take the half space, the half interval AB, capital A, capital B, right? So this is A here, and this is B. We have this half interval, and then we can take all the half intervals on this half interval, right? Like this one, A and B, or I don't know. Didn't change. Here. Or this one, A and B, all right? So we can take all the possible half intervals here, and we get a semi-ring. So this is a semi-ring, and we can show that, okay? Then, in such a way, we can get the minimal ring containing S, okay? Now, what else? Yes?
Does it matter that the small intervals which are included are including on the left and not including on the right? Like the way you wrote it, B is included, little b, but...
Is included?
No, in the definition on the left. So here you wrote...
Sorry. Yeah, it's not like this, it's like... No.
There would be a problem when you reach B, right? If you write it like this.
Like we had before?
Yeah.
Yeah, like we had before, it was wrong.
Yeah.
Yeah, this is the way. Okay, yeah, sorry. Okay, so the same kind of half interval that we have here, we need to get here. Otherwise, it doesn't work. Okay, so we have that, semi-ring, a ring. And then what do we know? That if we have a ring, and inside this ring we have something called the universal set, then this is called an algebra, right? So if we have a ring if we have a ring, and then we have the universal set, then this gives us an algebra, right? So we have a semi-ring, then we have a ring, then getting this new universal set, we get an algebra. And now we have an algebra, good. What else can we say about that? And what else did we talk about previous class? Let me see. We have that. All right. Yeah, and finally we define what a delta ring and a sigma ring is. So just a sec. I think we can change that here. Yes. So we define the following. No, it doesn't. Ah, okay. I see it. So we can define a sigma ring and also a delta ring. Okay? So a sigma ring is a ring which is closed under what? Under the countable union of sets. Okay? So this is closed under countable union of sets. This is a sigma ring. And a delta ring is closed under countable intersection of sets. Okay? So we define what a sigma ring is and what a delta ring is. And if we have this sigma ring and we have this delta ring together with some universal set, then we get a sigma algebra and a delta algebra, right? So from here, we can get a sigma algebra and also a delta algebra. Right? So the difference is that in this algebra we have the universal set. That's it. Now, we prove that if we have some sigma ring and we have here some delta ring, then every sigma ring is a delta ring, but a delta ring is not necessarily a sigma ring, right? We proved that. We gave some example about that. On the other hand, if we have a sigma algebra, then every sigma algebra is also a delta algebra, and every delta algebra is also a sigma algebra, right? So this is useful because if we want to prove something for a sigma algebra, maybe it's better for us to prove it so if we want to prove something for a sigma algebra, we can prove it for the delta algebra, and the proof we apply it also for the sigma algebra because they are both the same, right? Equivalent. Okay? So we want to prove something here, we prove it here, so it means that we actually prove it here. That is why this is useful. And that's all we know. This is all we did last time. Okay? Do you have any question about this? No? Okay. Good. Now,
I had one question, sorry. If you go back to just like a regular, like the third point of an algebra, the third axiom of an algebra.
Of a sigma algebra, yes.
Sigma algebra, yes. So just to understand, it's a collection we're looking at on the left side, right?
Yes, this is, so this means set A1, A2, AN, and so on. Countable collection of sets.
But it can be any combination of like, of each of them, right?
Yes, of course.
So it's not just like A1, then A1, A2, like it's actually like, it could be any.
It could be any element of F.
So
And if, yes, look, if you have A1 and A2, and they are elements of F, the union of A1 and A2 is also an element of F, right? Okay, so you can take A1, A2, and A3 is actually A1 union A2. Yes, why not? Because this is an element of F, right? So you need to take all this countable sequence.
But you could also take A3 and A2 without A1, for example.
Yes, and so on. So you need somehow to define this sequence.
Yeah.
Because this is a sequence, a countable sequence. So some law that this sequence follows. And then you get an infinite but countable sequence, and that's it, all right? For example, what do I mean with this? For example, we have this. So this is a half interval like this, right? We can actually define the open set A and B using this. How do we do that? This is going to be the following. So how do we find this relation here? So we have the open set A and B. All we have to do is to take A, and instead of taking B, we need to take B minus 1 over n. The countable union from n1 to infinity. And this gives us this. Yes?
And n is the number of...
N is from the numbers from 1 to
Okay.
the natural numbers. Right? So this gives us this. Yes? Right? So every time we are closer and closer and closer and closer, and we get the union of all of this, and the union of all of this are all the real numbers before B, but not including B. So this is why we need this. We need this because we can define this, for example. So we can get a semi-ring like this, but because we have this property, then a semi-ring of half spaces will contain also all the open sets and the closed sets and so on. So this is why this is very useful. This is why we need it. Okay? Yeah. Good, great. Now, let me define something very important. So this is a definition, and this is called a Borel sigma algebra. Did you listen about this before on calculus or something? So, like I told you before, we can do something like this, okay? So let's take, for example, A here and B here. So the open interval AB. And let's take all possible open intervals here. All possible open intervals, right? Now, there exists a sigma algebra which contains all these open intervals. And this sigma algebra, the minimal sigma algebra, which contains this set, is called a Borel sigma algebra. Right? So this is the minimal sigma algebra on R, we are talking about the real numbers. We can actually define this on any dimension here, so Rn. So this is the minimal sigma algebra on R, which contains all the open sets. Okay, so again, we have all the set of all the open sets. Okay, we have the set of all the open sets, and we can define some set of including these open sets and something else, and this will be a sigma algebra. And the minimal sigma algebra, the minimal set, which is a sigma algebra and contain these sets, is called a Borel sigma algebra. And this is very important because we will define a random variable will be defined on Borel sigma algebra. Okay, so for example, if we talk about here f, then we will be talking not, so now we are talking about this, right? But in about 2 lectures, we will be talking about this. So we will move from the sigma algebra on omega to the Borel sigma algebra on the set of real numbers. And omega for us will be the set of real numbers. And this will be our new probability space. And we will actually forget about this, and we will work only with this, because we will work only with random variables. And random variables are defined over here, okay? So that's why this is very important, Borel sigma algebra, what the Borel sigma algebra is. I recommended you some videos on measure theory on YouTube. Please check that videos, because you will understand very good the meaning and the definition of a Borel sigma algebra, okay? Maybe it's not very clear right now, but you'll get it, okay? Good. So this is a Borel sigma algebra, all right? Now look, we had this, let me change just this color, the color of this, yes. So we have the semi-ring S, and if we have this semi-ring S, we can construct the minimum ring containing S, which is R of S. We can build it very easily. And from here we can get some algebra which contains S. Good. Now we need somehow to get from here to a sigma algebra, because our final goal is to define a sigma algebra, how to construct this sigma algebra. This is what we need to do right now, okay? So we already know S, R of S, and this algebra, and now we need to get the sigma algebra. How do we do that? Well, we need to define what the measure is. Measure. So what's a measure? A measure is a function, right? So we will get, so let S be just a semi-ring, right? So we have the semi-ring, then the function M, right? A function from S to the real numbers from 0 to any number, but not including infinite. So the measure is not infinite, okay, right now. It will be, but in other cases. So we have a function from S to the set of the non-negative real numbers, okay? Let S be a semi-ring, then the function M, yeah, such that for every element of SA, A1, A2, AN, such that A is equal to the disjoint union from I1 to n of AI, right? It follows that the measure, it follows that the measure of A is equal to the countable sum of the measure of AI from I1 to n. This is n. Okay? So if we have S, the semi-ring S, we have some element A, and A can be expressed as a disjunctive union of some elements A1, A2, An, then we can define the measure of A as the sum of the measures of each of these subsets. Okay? And this is a measure. This is the definition of a measure. Okay? A function, right? Measure. Measure is somehow the general definition of volume. All right? So if we have, I don't know, some area, some square here, so we look at the area of this square is the measure of this thing here, right? So the measure of this set A is just the area. If we have something in the three-dimensional space, then the volume of this is the measure of it, right? And for example, what's the measure of the closed interval A and B? It's just the distance between them, so B minus A, right? So we can define it like that. So this is just one measure. We can define it very different measures. But this measure from here, this is the Lebesgue measure that you know from analysis and from calculus, right? The measure of the closed interval AB is just B minus A, okay? So measure is the definition of volume, the general definition of volume. And now, why do we need this? Because over here, right, when we have here, this P from here, this is the probability measure. So this is a measure, right? But not just any measure, but it's a measure which we call probability measure, and the difference with all of this is that it goes from 0 to 1. So that's the only difference, but all of this is absolutely the same. So the probability measure is a measure defined from S or from any set to the set of the real numbers from 0 to 1, right? But I'm giving you just the general definition of a measure. Now, this property from here, this is called the additive property. Right? I think it's clear why. Well, because we are summing some things. So this is the additive property. But as you can see here, how many elements do we have here? We have n elements, so finite number of elements. And of course, since we need to work with sigma algebras, we don't need finite number, we need infinite numbers. So there's something called sigma additive measure. So every measure has to be additive, all right? Every measure has to be additive. But some measures can be sigma additive. Could you please tell me what do I need to change here to make this measure sigma additive? What do you think? So if this is just additive, right? Like for example, an algebra, we have a finite set of elements, so it's closed under the finite union. And the sigma algebra is closed under the countable union. Then if we have that this is the additive property with finite number of elements, then this measure is going to be sigma additive if
well, you need infinite A. Well,
yes.
Infinite
So we need to write exactly the same until here, right? And then you need to write such that for every A and A1 A2, and so on, so countable number of sets, such that A is equal to the disjunctive union, countable disjunctive union of this, then we can define that the measure of A is the sum from I1 to infinity of the measure of AI. So if this is true for a measure, we say that this measure is sigma additive. All right? So we have a measure, and a measure is a function, and we have this property called additive property. And then we can extend this property to the sigma additive property. Good. And what can we do with all of this? And of course, we need all of this because of what I was talking about here. Well, actually not here, but here. Why do we need that? Because if we want to find the measure of this, we can define the measure of each of these sets, right? Then if we want to find the measure of this, it's going to be this infinite, the countable sum of the measures of these sets. So we need this probability measure to be sigma additive because of this, right? Somehow, okay. Now, we have that, good. Let me see, what do we need next? That. So we need a couple of lemmas. Let me write that. So lemma number 1. So for this one, it's just the following. If we have a semi-ring S, right? Yeah, so we have that M. So let M be a measure. Don't forget about this A here. So M is not unique. So there's not exist the measure of something. There exists a measure because we can define different functions on something, right? So there are different ways of measuring something, right? So for example, for the closed interval AB, we can say that this is B minus A. Yes, but we can say that this is f of B minus f of A, sorry, not f, but phi, where phi is just a function, some function. And this function is something that we will call actually the cumulative distribution function. But we will see that later, okay? So there's not just the measure, there's a measure. So let M be a measure over S. S is the same, is some semi-ring, right? Then yeah, if we have these sets A, A1, A2, AN, such that A is a subset of the union of AI from I1 to N. All right, so what does it mean? It means that we have something like this. So we have A, this is A, right? And we have some covering. This covering from here is like this. So this is A1, this is A2, and this is, for example, A3, and so on. So the union of these sets are covering the set A, right? So we have that. So what can we say about the measure of A? The measure of A, of course, is going to be less or equal to the sum of the measures of each AI, right? I mean, this is kind of obvious, okay? You can see it, yes? Okay, good. Yeah, this is kind of obvious, but we need to talk about it because we will need it to prove something. So this was lemma number 1. The lemma number 2 is as follows. Again, exactly the same, but so we have, so M is a measure over S, and we have these sets A, A1, AN, but now we say that such that AI, the intersection of AI with any AJ is empty for any I and J different. So they don't intersect. So these sets are don't intersect. And such that the disjunctive union of these sets from 1 to n of AI is a subset of A. Right? So now we have the following picture. So it's different. So in this case, we have something like this. So we have, this is A1, this is A2, and this is A3, something like this. And all of them are included on A. Right? So of course, then we get that the measure of what? Of A is greater or equal than the sum from 1 to n of the measure of all of these things, right? And this is kind of obvious as well. Yes? This is not there, so from here you can see it. Here the measure is bigger, and here the measure of A is smaller than the union, just like that. Good. Why do we need that? Because using this, we can prove that, that this measure from here is sigma additive. So we need to prove that the measure, so that the measure of open or closed intervals A, B, the measure if is B minus A, that this measure is sigma additive. This is not trivial at all, and we need all of this to do it. Oh, this is impossible. Okay, so look, we have this. So we define two things. First, this one. So that if we have some set A which is covered by some other sets, then the measure of, here is, let me just, so 3, can change it to 24. Here we have this and number 3. Okay, so that if the union of these sets are covering A, then the measure of the sum of the measures of each of these sets is going to be greater than the measure of A. We can see that from the picture, actually. And now, if we have that A is covering the disjunctive union of these sets from here, then the measure of A is going to be greater than the measure of the disjunctive union of these sets. And that we have it here. Okay? So we have these two lemmas, which are going to be very useful a bit later. And now we can't, we have the following lemma. So this is lemma number 3, not number 3, I think. And that's the following. So from a semi-ring S, we defined a ring R of S, right? So we have S, then we have R of S. In S, we have the measure M, okay? This measure M that we've been talking about. Now, we can define a new measure of R of S called mu. And how are we going to define the measure for every set of R of S? So if A is an element of R of S, right? It means that A is the disjunctive union of some elements of S. So this AI from here, let me see. Each of these sets are elements of S, right? And this is an element of R of S. Yes, by definition, this is what we define, how to get R of S from S. Now, how do we define then mu? Of course, from here, we can see that mu of A is going to be just the sum from 1 to n of mu of AI, right? So we are going to take this measure M defined on S, and we are going to get the measure for every set of R of S, okay? So it means that, again, we have this ring, and we get the, we have the semi-ring, and we get the ring. We define this measure M of the semi-ring, and now using this, and we can define the measure mu of R of S, okay? That's it. Again, all of these have to be proven, but we're not going to do it. And what can we say about that? So the first thing that we can say, and this is actually a theorem, I think, I don't remember if it's a theorem actually. Yeah, I think it's a theorem. It's that if M is sigma additive, then what do you think? Of course, mu is going to be sigma additive. Okay? So if this measure over here is sigma additive, then this measure mu is going to be sigma additive as well on R of S. Okay? Good. Now, how do we apply all of it? How do we apply all of this theory? For example, we can prove the following. And let me look at this because it's not trivial. So look. So let's prove. So this is some kind of exercise or something. So let's prove that M, which is defined, okay, no, let S, so this is the semi-ring of all intervals. Okay, so S is the semi-ring of all intervals. We are going to write it like this. A and B. And it means, so this includes, so this means AB closed, AB open, and half closed and half open, right? So A. So we take all the possible intervals in A and B. Okay, here A and B are just real numbers. So we take all the possible intervals and we applied the following measure. The measure of A, B is going to be just B minus A. Okay, so the measure of any closed or open interval or half closed, half open, and so on is the same, just B minus A. This is a measure, right? And we can easily see that this measure is additive. But let's prove that M is sigma additive. Right? So this is not trivial, of course. Let's show it over here. So what do we need to prove? We need to prove that if we have some collection, some countable collection of intervals, then the measure of the union is the sum of each of the measures of these intervals. Let me write it. So look, if we have that A and B, so the interval AB is just the disjunctive union from 1 to infinity of some ai and bi. So we have defined this, okay? So AB is the countable disjunctive union of some intervals AI and BI, right? So we need to prove that the measure of A and B is just the sum from 1 to infinity of the measures of each of these sets. This is what we need to prove. Let me write it like this. So it is true or not. If this is true, it means that this measure is sigma additive. If this is false, it means that it's not, right? So how do we prove it? All right, so look. So let's look at this side. Let me see. Yes, we have it like this. So we have A and B. This is A, and this is B. Okay? So let's take a new interval alpha and beta, like this. Okay? And so this is the first step. And we can see that, of course, alpha, the closed interval of alpha and beta is a subset of A and B. So here we have the closed interval, and here we have any. And from there we can see that the measure of alpha and beta is greater than the measure of AB minus epsilon over 2. All right, so look, we have this, yes, we have this over here. And now if we take this minus here and here, so we take this A and B, we make it smaller, so minus epsilon over 2, then we can get here it will be like A and B, but minus epsilon over 2, somehow, okay? So the measure of this alpha and beta is going to be greater than the measure of this A minus B, B from AB minus epsilon squared, minus epsilon over 2, okay? Good. Now, and for the second step, we need to do something like that, but for the little intervals here. So in that case, we need what? We need here we have AI, and here we have BI, okay? Well, actually like this, not like this. And here we can have the open sets of alpha I and beta I. We can see that they are greater, right? But of course, we need to make it smaller now, this. How do we do that? So we can see that alpha I and beta I is a subset of the interval AI and BI, right? But we can make that the measure of alpha I, beta I is less than the measure of AI, BI plus epsilon over 2 to the I plus 1. This is just less. Okay, so we take this length and we make it bigger because we are summing up this number, right? Epsilon over 2 to the I plus 1. So this will be bigger, and of course the measure of this, of the new A, I, and B I will be greater than the measure of alpha I, beta I. This is what we have this, what we have here. So the measure of this will be greater than this. Okay? Good. Now, what can we do with all of this? So look, just a sec, yeah, black. So we can write the following. Come on. Yeah, alpha and beta. The closed interval of alpha and beta is, of course, a subset of the countable union from 1 to infinity of all these closed open intervals. Okay? So I hope this is clear. So look, we have that alpha and beta is smaller than A and B, and every alpha and beta is greater than A and B. Then if we unite all of these alpha and beta, of course they are going to be greater than alpha and beta itself. So we obtain this. Okay? And now so what does it mean? So how do we call this? We call this a covering, right? A covering of the set of this closed interval alpha and beta. This is a covering. And we have a countable covering. And there's some theorem on calculus that I don't remember the name. Yeah, the Borel theorem. Borel theorem. So there's some theorem that you should have proved, maybe during the first year, that if you have this, then there exists some finite covering of alpha and beta. All right? So if you have some countable covering, then because of some, so there's some theorem from calculus. I think it's the Borel theorem or something like that. That makes sure that if we have this countable covering, then there exists some finite covering. So it means that we can change this infinite here for some n. Okay, so there exists this finite covering. So we can change this. So alpha and beta is a subset of some finite union of this alpha I and beta I. Okay, we can get that. How do we use this? Well, we just need to do the math. Now look, the measure of A and B, right, of the interval AB, let's remember that this is closed, open, and half closed, half open, all right, is less than the measure of alpha beta plus epsilon over 2, right? We have this from here. So we just take this to here. So we got that the measure of A and B is less than this plus this. Okay? Now, what can we do? What can we say about this? Look, we have this, right? So we have that this set has a covering, and we proved well, we didn't prove, we have a lemma that if we have a covering, then the measure of this set, so the measure of, let's call it A, is less or equal than the measure of, let's call it B. Right? Because this is a covering. And then we have that this is less or equal than the sum from 1 to, let's call it K. I had here N, but we can show it by K. It's better to say K. Of all of this. Right? Plus epsilon over 2. So we have that. And then, of course, this, so we have this finite sum, and of course this is going to be less or equal if we change this K by infinite. So let's do it. Like this, right? Now, we have this, and we know this. Wait, this. The measure of each alpha I and beta I is less than all of this. So we can put it here. And we get the following. So we get that this is less or equal than what? This is the sum from 1 to infinite of the measure of AI, BI plus the sum, right? From 1 to infinite of what? Of epsilon to the 2 to the I plus 1. Plus epsilon over 2. Okay, and what is this? This gives me epsilon over 2. This is a series that you can compute easily, right? And finally, we get that this thing from here, then so the measure of what? Of A and B is less, right? Than the sum from 1 to infinity of the measure of AI, BI plus epsilon, right? So this is epsilon, but epsilon is any, so epsilon is any number greater than 0. Then it means that we can just don't write it, and the inequality is going to be exactly the same. So we obtain this, that the measure of this is less or equal, yes, than the measure of this sum, right? And what do we need to prove? We need to prove that they are equal, and we have that this is less or equal. So we still have to prove then the measure of the interval AB is greater or equal than the sum of I1 to infinity of the measure of AI and BI. So we need to prove this, and if we prove then, so we already proved this. And if we prove this inequality and this inequality, then we get that they're equal, right? How do we prove this one? We already know. What do we know about this set? This set and all of these sets. We know that, sorry, let me write it in color. We know that the interval A and B is just what? The disjunctive union of all these little intervals. Yes? And we show, because of a lemma, right, that from here follows this. Because we have covering of this set, so this is so this set is going to be greater or equal than this one. Okay, let me find it here. It's not here. No, it's over there. Just a sec. Almost. Yes. So this one. So we use this lemma here. So we have this in our case. We don't have subset or equal. We have equal. But what's the difference, right? Because equal is over here. So it applies. So it means that this inequality applies. And we can apply it to our case right here, right? This, so it means this. So we conclude that the measure of AB, so of the interval AB, just the sum of the measure of every AI, BI from I1 to infinity. So it means that the measure is sigma additive, right? So M is sigma additive. Now we prove it. Okay, so again, this measure here, and this is the classical Lebesgue measure that you know from calculus. This measure from here is additive, we know that, but it is also sigma additive, but that's not that trivial, all right? So to prove that this measure, so that if you have A and B, and the measure of A and B is equal to B minus A, to prove that this measure is sigma additive, you need to show all of this. So it's not that trivial, right? So additive and sigma additive are different things, and you have to define really good the difference, all right? Good. Let me see how much. We have 15 more minutes about for the lecture. Okay, good. So we have that. This is a measure. Good. Why do we need all of this? Again, we are trying to get, again, let me write that over here. So we have the semi-ring S, then we got the R of S, the ring, then we have an algebra, right? And from this algebra, somehow, we need to get the sigma algebra. And we will do that using the measure, the definition of a measure over this ring here, okay? Good. Now next, let me see, what else do we need to do? Now we need to define something called the outer or exterior measure. I'm sure that you know this from calculus, that's for sure, the outer or exterior measure. So when you were defining an integral, you had to somehow do the following. So you need to, for the integral from a to b, you had two cases, right? The first case is this one. I don't know, something like this, okay? So the interior measure, right? So this area, the sum of these areas, you call it the interior Jordan measure, right? And then you used this one. And you call it the exterior Jordan measure, right? And you say that the measure exists, is defined if the interior measure and the exterior measure coincide, right? They are the same. In that case, you define the integral, this area from here, right? We're doing something like that, but more general, okay? So there are two different measures. The first one is the, okay, yeah. So the Jordan the Jordan exterior measure. So first thing that you have to know is that an exterior measure is not a measure. It's like an ex-girlfriend is not your girlfriend, right? So if the word measure is here, it doesn't mean that this is a measure. Okay, so this is a trick question that you will get in your exam for sure. Is that exterior measure a measure? No, it's not. Why? Because it's not additive, and you will see that. All right, so don't forget about that. An ex-girlfriend is not your girlfriend, right? So we have the Jordan exterior measure. So let's take any, for any, before that we need to get the following. So some conditions. Let me write that conditions over here. First, we have a semi-ring S, and we have a measure on S, which is sigma additive. So we have S, and we have M, which is a measure on S, and this measure is sigma additive. Then we have R of S, right? The minimal ring containing S, and then in this set, on this ring, we have defined this measure mu, right? That we already defined before. And what else do we need? And we have an algebra. So, and E is an universal set on R of S. Okay, so we have an algebra. So we have S, then we have R of S, and on this R of S we have the universal set, and then this R of S becomes an algebra. Good? Now, let's take any set from E, right? Absolutely any set. So E, for example, is this interval here. So this is E, the universal set, which contains all the other elements of S. And this is A, for example. A, right? A maybe is an element of R of S, maybe it's not. So maybe, so A, let me write it here. A is not necessarily an element of S. Okay? Maybe it is, maybe it's not. All right? So it's any element. We're taking all the possible all the possible subsets of E. All right? And now we can define the outer Jordan measure of A is going to be the infimum over all the coverings, the finite coverings, A1, AN, such that A is a subset of the union from 1 to n of AI, and the sum of the measures of AI, I from 1, sorry, yeah, we don't, yeah, okay. Let me write that over here so that it's better. Again, so the outer measure, Jordan measure of a set A is just the infimum over all the possible coverings. So A is a subset of the union I, and we just take the sum from 1 to n of the measure of AI. These are elements of S, by the way. So again, what are we doing here? We have this A. Again, maybe A is not an element of S. So this is for the general case. And all that we have to do is to take, for example, all these A1, A2, A3, AN. So we take a covering, this covering, each of these AI are elements of S, and then the external measure is going to be just the sum of the measures of all of this, okay? This is called the Jordan external measure. This is the first one. But there's a second one, of course. And the difference, so this is called the Lebesgue external measure. And this is almost the same, and we write it like this. So the conditions are the same that we have here. So we have for any subset of E, we have that the external Lebesgue measure of A is just the infimum over all the countable coverings. So we have A1, A2, and so on. So we have an infinite number of elements of S here. Such that A is a subset of the countable union, here infinite AI, and we have to sum up from 1 to infinite the measures of AI. So we have the Jordan and the Lebesgue, and the difference is that here we have an infinite number of elements of S, an infinite covering. And here we have a finite covering, right? N is as big as you want, but it's finite, okay? And here we have infinite. And to finish, I would like to ask you the following question. So what if we want to find the Jordan, for example, the Jordan external measure of the set. Let's take the set of all the rational numbers between 0 and 1. So the rational numbers between 0 and 1. Sorry, I don't, not like this, but here, this is here Jordan measure of Q intersection with 0 and 1. What do you think? So we take all the rational numbers from 0 to 1, and we want to find the measure of this set. How much? this is going to be 1. But the measure, the Lebesgue exterior measure of this set is going to be 0. Why? How many rational numbers do I have from 0 to 1? I have infinite numbers, right? For example, and then what? So for example, I have here 0, I have here, I don't know, 1 over 5, here I have 1 over 4, and so on, right? These are rational numbers and we have infinite numbers. If we take the Lebesgue measure, then we need to take an infinite covering. So we can take this covering here. Then for this one we can cover it, and so on. So for each number we can cover it. We can cover each number with a set. The measure of this set is going to be 0, right? Because this is a point. So we can't cover every point, and the measure of every point is 0. So the sum of infinite times 0 gives us 0. This is the Lebesgue measure. But if we want to find the Jordan measure, we cannot do that because we have infinite number of rationals, but we have a finite covering. So at some time it's not possible to do that for each point. So we get that the sum is 1, right? And now we can prove using this that the Jordan measure is not a measure because the measure of the rational numbers from 0 to 1 is 1, and also the measure of the irrational numbers, so let me write it like this, irrational numbers from 0 to 1, this gives us 1 as well. And so we obtain that if we have all the real numbers from 0 to 1, of course this is going to be the measure of the rational numbers and the measure of the irrational numbers, and we get 2. So the measure of all the numbers from 0 to 1 give us 2, if this is the Jordan measure, and this is not true. So this is not a measure. The Jordan measure, the exterior Jordan measure, is not a measure. On the other hand, here we have 0 for the Lebesgue measure, but for this set we get 1. So we get 1 plus 0. So we get that the Lebesgue measure of all the real numbers from 0 to 1 is 1. And that's okay, because that's what we need, okay? That's it.
All right, guys, so let's start. So first of all, so Kutika was here, but she left. Let's wait for her, maybe. I mean, let's see, she appears. Gomez Santiago is sick, as far as I know. He's ill. David, that's you, right? Rohan, that's you, right? Daniel, he wrote to me. Monica is not here. David, number 2 is not here. Who is David?
My name is Ashish. David is my surname.
Ah, yeah. No, wait. Then that. All right. So you are Ashish, David Ashish, but your name is Ashish.
My first name is Ashish. Last name is
Ah, okay. So Ashish and David.
No,
Yes. He's David.
He's followed. David is middleman.
Yes.
Ah, yes. You told me. You are
Mora.
Mora.
Yeah.
Mora.
Follow.
Follow.
I think it's like short and what's the full name?
Before they Mora Folua.
More. Ah, all right. Follow.
Folua, yes.
Yeah, I'm sorry, but it's difficult for me. So actually, yeah, my name is Carlos, but that's not the name that like everyone calls me. So I'm Juan Carlos. My full name is Juan Carlos. It's okay. So and the coffee, that's you, right? Okay. And Mikhail, so you are here in Russia. Let me write that. And Gabriel was here, but she's left. Okay, good. So, yeah, before starting with the homework, I would like to recall a problem that we had before that we didn't solve last time. Okay, so look, if you remember, this was like the problem number 4 from homework 1. So this is from homework 1, like the problem number 4 or 5. Not sure, right? So what we have 2 guys. The first one have 3 dice. So we have guy A and guy B, right? So the first one has 3 dice, and this one has 2 dice. Yes? And they roll these dice at the same time and independently. Yeah? Okay. And we need to find the probability. So, and the game finishes when? Yes.
First person gets.
Yeah, when someone gets 6.
I think when 8 gets 6.
Yeah, well, that's the probability that we need to find, right? So we need to find the probability that A gets 6, but B doesn't. Right? That's the probability that we need to get. So that in some of these times, so we have k times, for example, at this time k, the person A got 6 and person B didn't, so A won. We want to find that probability. So how do we get that? All right? And this actually was more complex than I thought, but we have. So look, first, let's define the following. The following event, AI. So AI means that someone got 6 in in the kth time that they rolled these dice, someone got 6. All right. So this is AI. Maybe A, maybe B. We don't know that. Someone. Now, let's define the following event also. DK. This is the event that nobody won before the kth turn. Alright? So nobody won. So it means that for every AI before k, so from I1 to k minus 1, nobody won. Right? So the complement of AI. Nobody got 6 before k. We have that. Okay? And then we can define the following events. CK is that player A got 6 at the k turn. Right? And say this would be BK, well, it's not very, BK is better. Player B got 6 at the k turn. Okay? So we have that. And we want to find this probability. Right? So, in which case, we have that. So let's fix some k. So for any k, we need this. We need that A got 6, so CK, right? We need that B didn't get 6, So we need the intersection with the complement of vk, and we also need that nobody won before. So vk. We need this, right? And we need this for all possible k. Wait. So we need this for some fixed k, and if we want to find this probability, right? So this is the probability that A wins on the time k. But if we want to find the probability, yes?
What is decay again, please?
Decay is that nobody won before k. So before k, everyone got numbers different from 6. And now, since we want to find the probability that A won, then we need this for all possible values of k. Right? So we need the union of all the possible values from k1, well, to infinity, right? Because this can go forever. We need to find this probability.
I think we came to this stage last class. We didn't integrate. We left dancing.
Yeah, but here, so how do we find this? Yeah, how do we find the probability of the union of these intersections? And this is the key question here, right? So is this part understood for everyone? Yes? So this is the event, this is the probability that we need to find. So how do we find that? What do we know about the events CK and BK? They are independent, right? So we know that BK is independent from CK. Good. Now, now let's take this event from here. No, before that. Wait. Yes. Just a sec. This is an event for k, right? For example, 5. For k equals 5. Now, what if we have k equals 6? What happened with this event for, let's say, k5? And now this event again, so ck intersection bk complement intersection with bk. But for all of this, for k6, this event and this event are independent. Sorry, no, this is not true. They don't intersect. They don't intersect. Why? Because if this happens, it means that A won here, right? But if this happens, it means that nobody won before 6. But here somebody won at 5. So this and these events don't intersect. The intersection of these events for different k is empty. Alright? Why do we need that? Because we need to find the union, the probability of the union. And what do we know about the probability of the union, right? So if we have the probability of A union B, is the probability of A plus the probability of B minus the probability of the intersection, right? But this is if A and B intersect. Now, if they don't intersect, all that we need is the probability of A plus the probability of B. And this is what we are going to do here, right? So we know that they don't intersect, so we can write this. The sum from k1 to infinity of the probability of ck intersection bk complement intersection with dk.
So can you repeat once again why for different values of k this term is independent?
Because here, for example, for 5, it means that in k equals 5, A 1. Right? Here we have that dk, and dk means that nobody won before 6. So this is not possible because in 5 A won, right? So they don't intersect. So good, we have that. We have this. Now, how do we compute that? What do we have here? We have the probability of the intersection.
Probability of CK times probability of DK giving D.
Times what do given you mean conditional probability? Yes. So we let's compute each of this. Well, so this is equal to the sum from K1 to infinity of the probability of CK complement, intersection DK complement, conditional probability, so given DK times the probability of DK. Yes? This is just by the definition of conditional probability. Right? Yeah, good. So, how do we find this? So, what about this event and this event? They are independent. So, if nobody won before K and somebody wants in K, these events are independent. Right?
Somebody won in K depends if somebody didn't win in the last round.
No. I understand what you mean, but so look, this event means that at some K, A won, right? And this event means that before K, nobody won. So these are two different experiments. They are independent. Do you see why?
Yeah.
Okay. So it means that this is equal to what? So the probability of A given B, if we know that A and B are independent,
It's going to the probability of CK intersection DK times.
again please.
CK multiplied by 1.
So without this, right? What do you mean? So the probability of CK intersection DK complement. Just like that, right? So we don't care about decay because they are independent. Okay, good. So we have that. Now, let me write that over here. So this is the sum from K1 to infinity of the probability of CK intersection D complement times probability of DK. Good, so all we have to do now is to find this probability and to find this probability, right?
The first one is probability of CK times probability of
Yeah. Yes. So this is what? So this is the probability of CK times the probability of the complement of DK. Yes, because they are independent. So what is the probability of CK? So the probability that A got 6
that's
and he has 3 dice. 3?
6 times n just 2.
So look, 5 over 6 to, cube means that he didn't get 6. And then we got 1 minus this. Good, right? So it means that A got 6. In which one we don't know, of course, because we have 3 dice. So we need to look at the probability that he didn't get 6 at all and just take 1 minus all of this. So this. And now we have to find the probability that B didn't win. So the probability that he got all the numbers that he got are different from 6. So 5 over 6 squared because he has 2 dice.
But the question didn't say anything about he mustn't get 6 in the other two.
Yeah, because that's the probability that we are looking for.
But like he could get 6, 6, 6.
A gets 6, but B doesn't. So B cannot get 6.
Oh, I thought the 516 square was for the other two dice.
No, are for the dice from B, right? So we have this, good. And what about the probability of decay?
That's 516 raised to the power 5.
The probability that nobody...
Raised to the power 5k.
Wait. Nobody won. Ah, yes, so this is 5 over 6,
Raised to the power 5.
5. Yes? Because we have 5 dice. So the dice from A and from B. So if we didn't get
6 in any of them.
yes.
But
Uh-huh.
we need to do that k times. So
Yeah, and we need to multiply this by k minus 1? What? No? By k minus 1 times?
yes.
Okay. Good. Then, finally. Well, finally we have to compute this sum. So, so this is some number. Let me write this number out of the sum because we don't need it. So we have 1 minus 6, 1 minus 5 over 6 is to the power 3 times 5 over 6 power of square, right? And then we got the sum of 6 minus k minus 1 from k1 to infinity. Wait, something is, let me, so I don't like something here. Just a sec. No, yeah, so we have this one. Okay, so what do we have here? Huh? One? No, why one? So look, let's consider all the cases. What if we have k equals 1? Then we have 1. Right?
It's just a geometric sum problem, right?
So
Yeah, it's a geometric series, right? So we have 1 for k1. What about k2? Then we have 5 over 6, and we have 2. So we have 5 here, right? 10 plus 5 over 6, and we have 3 for k3, so we have 10. And it to infinity. Infinity, right? And what is this? So wait, so let me remind you, 1 plus r squared plus r cubed, so on. This is equal to 1 over 1 minus r, right? You know this from your second year thing. So what is r in this case?
5 over 6 raised to 1.
So r in this case is 5 over 6. There, 5i? Yeah. Yeah? No? I mean, we have 5, 10, 15, and so on. Yes? So, well, I mean, to the 5. I is the number that change. So we have this. So the answer for this is 1 over 1 minus 5 cube no, but to the 5 over 6 to the 5. Yes? And then, and that's it, this is the answer. I mean, you can compute the final answer, and that's the answer. Alright? Yeah? I think it's alright. Yeah, that's the answer. So the final answer is going to be something like 91 times 25 times 25 over 6 to the 5 minus 5 to the 5. This is the final answer, okay? And that's it. So it is clear for you? Good, great. So this was the first exercise. Well, this was the exercise that we didn't solve last time. It wasn't that easy actually. And now let's start with the homework. All right. So who wants to solve the first one? You want it, right? You have a volunteer. All right. Which one is the first one? I already forgot. Let me check.
Homework 2. All right. Yeah, this is a good one. How did you try to solve it? Mm-hmm. Right. You have C. This is E, right? A minus D plus B. Mm-hmm. Yeah. Mm-hmm. Yeah, you can use that somehow. How?
And this will only be true.
Wait, so A minus D. Wait, no. A, B, and C, and you have 20. No, A minus D, and you have 21 possible values. You say? Because you have 0 minus 10, for example, and then you have 10 minus 0. So from minus 10 to 10. Yeah, wait, 10 is not is not included here.
Or we have a minus x plus x and
No, this, we have more cases.
And we have one other case. So it's much more complicated.
We have more cases, yes. So your idea is good. I mean, we have to use that the sum is 0, yes. But there's something else that we need to add to this. So we need to get some fixed number, not 0. 0 is useless, right? So the sum of the first part plus minus the second part is 0, right? 0 here is useless. We need to get some other number. We need to, I don't want to tell you the answer yet. So do you see some?
This approach, I have to forfeit it because I thought it was really two possible cases. There's another case maybe.
Which number? No, these are numbers from 0 to 9. So look, let's do the following. We have, for example, just write any number for A, B, C, D, E, and F. Any number. Great. Wait, you have 7 numbers here. Okay, we have this number. But, sorry. Write any number such that the condition holds. Sorry. So such that the condition holds. So create some number there. Cannot be what? I don't get what you mean. Why? Yes, yes.
And the minimum value of B can be 0 and C also can be 0.
Yes.
Also 0. Then if we subtract them, then there will be 27. So it cannot be greater than 27. So A plus B plus C minus B plus C plus F cannot be greater than 27.
Yes, but that's not enough. There's something else.
We can also find the minimum limit.
Look, wait. So what you say is okay. So look, for example, we have this number. So we have 10 here and we have 10 here. This works, right? Now, what if we take not this number, but 9 minus this number, minus 4. So right here. So 9 minus 4 is 5.
And then they will not
Wait,
be-
9 minus 1 is
Oh, minus all
8.
of them.
Yes.
Okay.
And this is, Okay, so we take 9 minus the first one here, so we get 5. Then we take 9 minus 5, and we get 4. And we take 9 minus 1, and we get 8, right? And in general, we can see the following. What if we take, so we have A, B, C, D, E, and F. Instead of writing D, let's write 9 minus D, and 9 minus E, and 9 minus F. And let's sum up everything. So A plus B plus C plus all of this. How much do we get? No. Why 0? We have 9. 27, right? And
The condition holds, right?
if the condition holds, right? So we need to work with the numbers that for which the condition holds. So look, so we have this, and for any D, there exists a unique 9 minus D. So, and actually we have here, what do we have here? So let's remember you first here. What if we have not only a surjection, but an injection and a surjection? So we have a bijection here, right? So we have a bijection between every D and every 9 minus D. So for every possible value like this, there is a unique number 1, 9, 0, 5, 4, and 8. There's a bijection. And what do we know about this? That the sum, so it means that the sum of all these numbers always is going to be 27. So let's sum up. 9 and 1, 10. And 9, wait. 9 and 10. Wait, what? Yes, this one, right? So
Can you remind me, is there any restriction that A must be 1 or greater than 1?
it must be any number, right? So we have here 10, and we have here 12, 13. No, wait, what is? No, 10. 8 plus b, 0, 10. Where's the thing here? This is 4, this is 5, and this is 8. Ah, this is 9, right? Yes, of course. So this is 9, so this is 17. Yeah, so we have 27. Yeah. So for each number, you can get this other number, which is a bijection. So we got a bijection here, and for this number, we got that the sum is 27. So we need to find all the possible tuples of numbers, which give us a sum of 27, right? Yeah? How do we get that? So first of all, and you continue. No, let's move back. Let's change here. First of all, how many possible outcomes do we have? So what's the... So we have 10 possible values for every time, right? So this is a million. So we have 1 million possible tickets of the bus, or what do we have, right? So we need to find, so this is the cardinality of this set of omega. Now we need to find all the possible tickets which give us a sum of 27. How do we get that? Hmm? What do you think? Do you remember your first year mathematical logic with Professor Dashkov, right? Huh? So there's something that you solve, I'm sure, something like this. So we have this equation here. So x1 plus x2 plus xm equals n. And you solve how many solutions do we have here, right? And do you remember the answer? How many? So this is basic combinatorics, right? From the first year. How many solutions do we have? How do we solve that? So how do we need to solve that? We have to think about the following. Each of these x is a box, right? So we have n boxes. This is the first one, the second one, and the m. And how many balls do we have in this case? N, right? 1, 2, n balls. Now the question is, how many ways are there to distribute the balls inside the boxes such that, well, it's just like that. How many ways are they to distribute these balls? Yeah, so that's something that we need to think about later. Right now, we don't care about this. So x1 can be 0 and can be n, and all of these can be zeros. So we can put all the balls right here. So let's do that. So the answer is what? How many? No, not n. How do we solve this kind of problem? So you can sit if you want, or you can continue. You can continue. All right. This gets a bit. So look, we can look at this as follows. So for, let me see. Huh? No, of course not. Now look, here. So how many balls do we have? We have n, right? N balls. So this is the first one, 2, 3. We have n. How many boxes do we have? M. So we can do the following. We can imagine that we have some, I don't know, some line here, some frontier, some line, and these lines divide the number of, so the box. So all the balls in here are the balls in box 1. We have another line, and these are the balls inside box 2, and so on. So how many lines do we have? n minus 1, right? n minus 1. For example, if we have just 2 boxes, sorry, so we have some balls here, some balls here. So box number 1, box number 2, we have just one line, right? So it means that we have n minus 1 lines. And the answer to this question is how many ways do we have to put these lines between these balls? And how many ways do we have? So we need to choose the position for these lines. So how many positions do we have? We have from n plus n minus 1, we have to choose n minus 1. Yeah? Sorry, did you write it like this or like this? I don't know, n plus n minus 1 and n minus 1. The same. I choose. I just don't remember which one to use. The second one is better, right? Yeah. Yeah. So we have n plus n minus 1. Choose n minus 1. So this is the answer to this question. And you know this from this course on combinatorics, right? Now we have something else. We have the following, that all of these values cannot be bigger or cannot be greater than 9, right? So they cannot be 10, 11, and so on. So what do we need to do? How do we solve that? What do we need to change over here to solve that? So we have some cases in general. So these are the total number of cases that we have, but we need to take out the cases that we don't want. Yes. So what kind of formula do you think we have to use? If we have to sum up and subtract something and so on. So this is the inclusion exclusion formula, right? So we have to look at the following event. So the event, well, not the event, but yeah. So let's consider. Well, So AI means that wait. and this is 10. We don't want that. Okay, so we need to solve the following. No, not any AI. So let's fix all the possible cases in which we have more than 10 balls in a box, all right? So to do that, what do we need to change? We need to do the following. Again, we have n boxes, right? 1, 2, n boxes, right? And we have x1 plus x2 plus xn, and this is equal to m, right? In our case, how many xm? Oh, in our case, m is equal to 6, right? So we have 6 numbers, and n is just 27. Okay, so for the general case, I mean, if we don't care about the restriction for xi, then we have that the answer is just 27 plus 6 minus 1, choose 6 minus 1. So this is 32, right? Choose 5. So this is the number of solutions for this equation if we don't care about this one. Now, let's consider the number of solutions in which how to say it? Just a second. So AI, it means that in box I there are more than 10 balls. 9. Okay, so we need to find the cardinality of the union from 1 to 6 of AI. So how many ways are there such that in the boxes there are more than 10? And then we need to take this number minus this number, and this is going to be the number that we're looking for. Now, how do we find this? The union of this. This is the sum from 1 to 6 of the cardinality of AI minus the sum of all the possible pairs of the intersection of AI and AJ. Now let's look at this number. So this number. For this number, we have to solve the following. We have 6 boxes. 1, 2, 3, 4, 5, and 6. And we have 27 balls, but we know that in one of them there is at least 10 or more. So all we have to do is to already put, for example, in the first one, 10 balls. 1, 2, 10. Right? And here, how many balls are we left? 2. So we have 17, right? Because we already put 10 balls over here. So we have 27. How many options, how many ways do we have to distribute this over here? Well, this is the number here. So in this case, we have that n is 17, right? Minus m, which is 6, plus 1, right? N minus n plus 1, and here 6 minus 1. So this number is 11, 12, 12, choose 5. Now we have to look at this one. And in this case, means that 2 boxes have at least 10 balls. So we have, what do we need to change for this one? We need to add another 10 balls for the second one, for example. Here, 10 balls. And how many balls do we have for this one? Well, 7, right? 7 balls. So, and we change it here. So we have 7 minus 6 plus 1. So we got that this number is 2, choose 5. Okay? Now, this sum, well, this is just the way of choosing the box which has more than 10 balls. So we have 6 ways. So this is 6, just like that, 6. And this is all the possible pairs of boxes that we can get. How many? 6 choose 2. Right? So we are choosing the balls which have more than 2 balls, more than 10 balls. Now, what about this one? A I, A J, and A K. What is this number equal to? Yeah. Exactly. So we have 27 and we need to put 10 in 3 boxes. So this is 0. This is just 0, right? Because formally we have to do it for all the possible, right? This is the inclusion exclusion formula. We need to do it for all the possible cases. But all of this is going to be 0. So we don't care about that. So we got this. Good. Then all we have to do is to take this number, 32 choose 5, minus this number. So so we get that 32 choose 5 minus all the possible ways in which that are not good for us. So 6 times 12 choose 5, here minus 6 choose 2 times 2 choose 5. And this is the number of solutions of the equation. So this is the number of solutions of x1, x6 equals 27, where each of these is less or equal than 9. Divided by 10 to the 6. Yeah, I think so.
What is this equals to?
So this is the probability, by the way, that we're looking for.
Do you have an estimate?
This number, if 55,000 something, should be.
No, like the estimate of the probability.
I don't know. Let me see. I think I have it.
No.
The probability is very small.
Very low. Because I also want to go back to my idea, and I got
Right.
to a very small probability, so I want to just.
Well, that's not difficult to get a very small probability.
Oh, sorry. I'm sorry.
5 seconds. Is that 2 choose 5? 6 choose 2
To choose 5, yes, I think. Yeah, because we have. Sorry. 5 choose 2. 5 choose 2. 5 choose 2, yes. Yeah, it's kind of useless. Why do we have a normal board? Anyway.
Is everybody done with this one? Yeah, you can still use Yes. So I'm going to go back to my idea of this one. So there are 4 possible cases in which this will be true.
then we have 0, 0, 0 for all the differences. We have minus x plus x and 0 in these three differences. Or we have three numbers, x, y, z, in which two of them are positive or two of them are negative.
Okay.
Or two negative. And we know that the total number of cases is 19 cubed. 19 possible here for each of these three places. So this 0, 0, 0 is just one case. And for minus x, there are only 9 different numbers. So that's 3 choose 2 to choose the two numbers which are going to be negative of each other. And there are 9 possible cases for that.
Two numbers, one number is the same, right? X.
No, two possible places. Like,
Ah,
let's assume that.
I
mean
get
by
it.
the
I get it.
differences.
I get it.
And
And you still have to 9. Okay.
And this x can be, there are 9 different numbers which we can use for x. And for these two other cases, it's by, you can say that they are bijective, so we can just say plus 2 times, and we need to choose which two differences will be positive or negative. And the number of possible cases in which you can sum them up, like 2 be positive and 2 be negative, because if one of them is positive, for example, and 2 are negative, we can only have something like 9. We can have maximum of 9, and the two others would be something like minus 5, minus 4, or something like minus 6, minus 3. Yeah. So for this one, we're going to have a second. Maximum is 9, and we need to have this one is very we can't have 1. So from 2 to 9, 7 cases. 7 cases, because it's going to have to start from 2. If it starts from 1, then there's only one case, 1, 0, minus 1. And that's already in this one where we have minus x and x. So it has to start from 2, in which none of the numbers are equals to 0.
I see.
And this can go from 2 to 9. And so I guess,
Sir, can you finish 10 minutes early today?
Hmm?
Can you finish 10 minutes early?
Why?
We didn't have lunch. We had physical education and then that class.
You have another class today.
Yeah,
Until 20.
What time is it? Well, let's see. Let's see if you. Let's see. All right. So look, I don't know. It looks you have to take into account many cases. So maybe. I mean, it's gonna be a little, a very small number, that's for sure. But I don't know. I don't know. I mean, what kind of omega do we have here? You know, so it's. I don't know if this is correct. Maybe it is, but I cannot tell you for sure right now. But of course, the idea is good. Yeah, that's for sure. All right. So.
the idea is correct.
Yeah, I mean, it could work. Maybe you have to compute it and to compare the answer. If you got the answer, yeah, then that's true. Yeah, that's a good idea, of course. I mean, this is not, the way I solve it is not the only one. We can solve it using different ways. There are like, I don't know, I know that there are like 5 or 6 different ways to solve it. But the one that I told you was like the simplest one, okay? Now, this one, the first exercise. By the way, let me check if I was correct about this one. The final answer over there. Uh-huh. 6, uh-huh. Yeah. How much do we get? So 6 times, why do we have here 12? It shouldn't be 12. We have 27 minus 6. This is 22, right? Not 12. And 15, 12, choose 5. Why? So for, no, 7. So the first one is 32, choose 5, right? No, this is for a different one. Minus 6 times 22, choose 5. Here is 22. Why here is 22? Because you have 17 minus. Here is plus m. Yeah, sorry. Here is plus, by the way, not minus. So this is n plus m minus 1. And here m minus 1. All right, so here it's not 12, but 22, and here is not 5, but 15. Okay, sorry about that. Yeah, no, 12 here, 12. Okay, n plus m minus 1, choose m minus 1. And that's it. Okay, so I confused this one. I told you this was minus, this is not minus, this is plus. All right, good. Now, next exercise, and everything else is okay. Next exercise is, let me see. Yeah, well, the next exercise is long, and we don't have that time. Okay, let's do the number 4. Anyone tried number 4? No? Is it what? The second? Anybody solve it? All right. Okay, let's solve the second one. Like the first one? No, they are different. Well, no, yeah, they are related somehow. How?
The sum is m. x1 plus x2 is equal to m.
Yeah, and how? Okay, let's try to solve it. So we have 2 dice, right? 2 dice. And in the first one, we have, so n-sided dice, right? So these are n, let's say n-sided dice. Okay? And we need to look at the probability that the sum, so let's say that in the first one we get the number k, and in the second one we get the number L, right? So we need to get that the probability that, no, it doesn't work like this. Let me just change this. We need to get the probability that k plus L equals some m, all right? So what's the probability for that? How do we solve that? First of all, how many cases do we have? N is, yeah, n squared, right? N squared. So n for the first one and n for the second one. So this is all the possible cases. Now, yeah? Okay, good. So we have k plus L equals m. So we have two different variables here, k and L. We don't know nor k nor L. But if we know, we know that the sum is m. So we can change these two variables just to get one, right? How do we get that? So we can say that we have k plus, and we can, instead of writing L, we can write m minus k, right? And this, of course, is going to give us m. So we don't need L anymore. All we need is k, right? So we only have one variable right now, and we need to work with this variable. So we need to look at all the possible k such that this equation holds. Yeah? So the first case, so we have two cases. So case number one, that's if m is less or equal than n plus 1. Okay?
Why n plus 1 and not a?
And not what?
Why not? Okay, I got it.
Yeah, so maybe you get n here and you get 1 here.
We cannot get 0.
So what do we do in this case? We need to get all the possible values for k. So k so what we need to find the bounds, the boundaries of k. How do we do that? K, of course, has to be between 1 and n. Yeah, so look, yeah. So k is less or equal than n, and yeah. And L, wait, how, just a second, I have this somewhere here. There's a tricky part here. How is it? Just a second. Right. So k. So k is between 1 and n minus 1. No way.
K cannot be n. Be something. Okay, let's say n is 10 and m is 2. We cannot have every k. We can only have k up to 1.
Yeah, exactly. So k must be less than n minus 1. Sorry, n minus 1. Right? So k may be at most n minus 1 because the second die is going to be 1. And in the sum we got m, right? So again, we have here n, have n. If we get here 1, which is the minimal number, then we should get here n minus 1 at most, right? Well, exactly. So k can be at most n minus 1, right? So for m be less or equal than n plus 1, we have that the probability that k plus l equals m is equal to n minus 1, n minus 1 n minus 1, right? N minus 1 over n squared. So all the possible values for k that we found. So from 1 to n minus 1. So n minus 1. Yeah, am I telling you the truth? Yes. Is this clear? Why? Good. Now we have the case number 2. In this case, m is between, well, 2n, right, and n plus 2. And for this case, let me write it over here. So we can see that k, first of all, k has to be, of course, less or equal than m, right? Well, that's kind of obvious, but we can see that. So look, we have the sum k plus m minus k equals m, right? And this is, well, this is k and this is l, right? So this is the value in the first one, this is the value in the second one. So we have that k can be at most m, but also m minus k, so l can be at most, sorry, here we have n, and this can be at most n. So the value in the second die can be at most n, of course, and the value in the first die can be at most n. And from here we get that k is greater or equal than m minus n. So k is between m minus n. So the difference, the number of k's that we need is just m minus m minus n, m minus n plus 1. N minus n, yes. Minus m minus n. So k is greater than m minus n. So k is greater than m minus n. And k, here is n. Come on. And then here we have n. Yes, no. N minus m minus n plus 1. So this is 2n minus m plus 1. So this is the number of k's such that the sum is going to give us m, right? So the probability that k plus l equals m for m being between 2n and n plus 2 is going to be 2n minus n plus 1 over n squared. And this is the answer. So the answer is that we have two cases. So this is the first case. So this is the first part of the answer. And this is the second part of the answer. So it depends on the value of m, of the sum, all right? Yeah, I got a little confused, but all right, we did it. Okay, is that clear? Okay, good. Now I think, we have 5 more minutes. Let me solve something fast and then we'll be finished, all right? Which one? Let me see. Okay.
5 minutes is spare, sir. Anything difficult, sir. It will take at least 10-15 minutes.
No, okay, the number 3. Exercise number 3. We need to prove that this is not true. A, B given. That this is false, right? That this is false, right? This is false. We need to prove that this is false. How do we prove that this is false? This is complicated. How do we show that that something is not true? You need to find some counterexample, right? So what if B is, for example, the sample space? So what is the probability of omega given A plus the probability of omega given the complement of A? No, B is omega. So what is the probability of the sample space? It's 1. It doesn't matter or something, right? So this is 1. And this is 1 as well. So we got that this is 2. That's it. This is a counterexample that we needed, right? So the probability of omega doesn't depend on anything. The probability of omega is 1. That's it. All right? Now, the second one, we need to prove that this is false as well. B given A, No, we just stated that way. So you see, right? So we need to show that this is false. And we have that B and A are any sets, any events. This is also an event, omega. If it doesn't work for this one, then this is false, just like that. So B given A plus the probability of the complement of B given the complement of A equals 1. How do we show that this is false? Well, we can take B equals A. Let's take B equals A. What do we get? With the probability of A given A plus the probability of the complement of A given the complement of A. 1 plus 1, 2, right? So this is false as well. So both these equalities are false. So if you want to prove that something is not true, you don't need to get something complex, you just need to get a counterexample, just like that. If you need to prove that this is true, then of course you need to prove it. This is the difficult way. But if you want to prove that this is not true, just get a counterexample, just like that. All right? And that's it. for today. I'll see you next class.